Why limit yourself to annual time periods and constant interest rates? This video explains how you can go beyond this rigid structure while enjoying the flexibility of the notation developed so far. In real life, you will face two questions. First, how to deal with interest rates when the time unit changes. And second, how to go from a constant interest rate to a rate that changes over time. Assume a yearly interest rate I. Which rate is then applicable to the mth part of a year? I star m denotes the rate applicable to such a period. Obviously, you can now calculate in two ways how much €1 at time 0 is worth at time 1. With a yearly rate, €1 grows to 1 plus I euro, but at the same time this should be equal to 1 plus I star m to the power m. This equality allows you, for instance, to go from a yearly to a monthly rate. Let's start from a given interest rate of 3% per year. You obtain the monthly interest with the transformation derived earlier. Here, a yearly interest of 3% is equivalent to a monthly interest of 0.2466%. You can verify this result by transforming back. 1 plus the monthly interest is how €1 grows over 1 month. Raise this to the power 12 and you find the accumulated value of €1 over 1 year. Subtracting 1, the initial capital, gives the yearly rate. That's again 3%. You can now deal with the second question. How to go from a constant interest rate to a rate that changes over time. In reality, interest rates are not necessarily constant over time. The so-called term structure of interest rates reflects the relationship between interest rates or bond yields and different terms or maturities. We wish to incorporate interest rates changing over time in our framework. Instead of working with a fixed rate I, the interest rate now changes over time. I0 is the rate applicable to the first year, between time 0 and time 1. I1 is the rate in the second year, and so on. €1 at time 0 is worth €1 at time 0. Thus, V00 should be 1. €1 at time 1 becomes 1 over 1 plus I0 at time 0. And to discount €1 at time 2 to the present moment, you multiply the discount factor 1 over 1 plus I0 applicable to the first year and 1 over 1 plus I1 applicable to the second year, and so on. The rates IK are given at the present moment, but they apply to a future time period. That's why people in finance would call them forward rates. This illustration demonstrates how discounting works when interest rates change over time. Here the rate is 4% in the first year, 3% in the second year, and then 2 and 1% in years 3 and 4. You store these rates in the interest vector. You create the yearly discount factors from these rates as 1 plus the applicable interest rate to the power -1. To quickly go from the yearly discount factors to multi-year discount factors, you can use the cum_prod function in R. This function returns a vector whose elements are the cumulative products of the elements of the original vector. Since €1 at time 0 stays €1, you extend the vector returned by the cum_prod function with 1. As such, the vector discount factors stores the discount factors to go from 0 to 0, from 1 to 0, and eventually from 4 to 0. Those were two big steps. Time to translate theory to practice.